All right, so our hero Robin Hood is trying to escape from the terrible sheriff of Nottingham and his band of henchmen. And to do so, he's hanging onto this rope right here while this chandelier used to be held down by something over here, which I guess he shoots an arrow at and cuts. So this whole thing is going to accelerate in this direction, taking Robin Hood with him up to safety, where he can run across the balcony and lead to his escape. Well, you don't think he's going to pull down the... All right. All right. I'll do it that way then if you want. All right, so this is more massive. It's going to obviously pull down. All right, so what I said a minute ago is this situation right here equates to what's known as Atwood's machine. All right, it's a classic physics problem. If we have two masses on either side of a pulley, a frictionless, massless pulley, assuming the tension to be the same in each case, then it behaves in a certain way that's predictable. Okay? So this Atwood machine, the idea of the Atwood machine is, if this is going this way, it's accelerating at the same rate that this is accelerating downward. So their accelerations are coordinated, so we just call it this direction, this way, the positive direction. And we straighten out the system. Remember, if we make the tension part of the system, if we make the whole thing the system, then interactions between two objects within the system have nothing to do with the acceleration of the system. Okay? So what we're going to do is we're going to take the two masses and we're going to do like this. Here's M, big M, and here's little m. See how I just took them and straightened them out? All right, pretty tricky. All right, and I'm going to draw a red dotted line around the system. And now the tension in the string, because we have put these two together into a system, is internal to the system and will not affect the acceleration of the system. The only things that will affect the acceleration of the system are forces acting across the system boundary. Okay? So what we do is we say that this force acting this way is big mg, and this force acting this way to the left, the negative direction, notice I drew it smaller, is little mg. All right, so we have these two forces working against each other, so that our net force is going to be the difference between them, and the mass that's being accelerated is the total mass of the system. Okay? So what we have, we can just simplify to this. We're just going to say this is m plus m, and we have mg working in the positive direction and little mg working in the negative direction. Do you see that simplification? We just represented the whole system now as one dot, okay? Just one aggregate mass. All right, so now we just employ the two equation strategy like we always would. Net force is equal to m, but what is the mass that's being accelerated? The entire thing, okay? Sometimes I make that what I call fancy m and call that equal to big M plus little m, but we'll just leave it as big M plus little m right here, times the acceleration of the system. This is just Newton's second law, true because it's always true, always the first of our two equations in the two-equation strategy. Now, our second equation we get from the free body diagram. And that's this right here, okay? Or up here if you want to think of it that way. So what are the forces acting on the system? What's acting in the positive direction? Big mg. And what's acting in the negative direction? Little mg. Okay, so we subtract it. So now setting those two equations equal to each other, we get big M plus little m, A, is equal to m plus m times g. Okay? Or is it minus? Minus. Whoops. Big M minus little m. Okay? So then the acceleration becomes very easy to find. Acceleration is equal to big M minus little m over big M plus little m times g. Now, notice that we haven't put in their numbers. We haven't put in any numbers. All we've done is generalize this. So now you guys realize that what we have here is a solution to every single Atwood machine problem because we solved it algebraically. We always know that the net force is big mg minus little mg, and we always know that the mass of the system is big M plus little m. So when we factor out the g, it'll always turn out like this. This is the answer to pretty much every Atwood's problem, until we start incorporating moments of inertia for the wheel, for the pulley, and then you find out that there's actually different tensions, but we ignore that at this point. All right, so now, just putting in the stuff for this particular problem, we know that big M was 195 kilograms, if I recall correctly, minus 77 kilograms over 195 plus 75. You guys are putting this in the calculator while I'm writing it, right? 75 kilograms. I wrote 77, it said 75, nice. Times 9.8 meters per second squared, okay? So dimensionally, how are we going to do here? Kilograms are all going to cancel out. We're going to have an acceleration term here, meters per second squared. So this acceleration should be, what do you guys come up with? 4.25 meters per second squared. All right, I know that's only the first part of it. That is the acceleration of the system. We still have to find the tension, but I'm going to break this up into two parts. Okay? Everybody follow that?